This is a regular FPV drone, and these drones are really fast and a lot of fun. But when I found out there's a whole category of these FPV drones that are nearly 4 times bigger than this, I knew I wanted to make one. But I didn't just want to buy the parts and put it together. I wanted to custom design nearly every mechanical component on this drone. So I spent over a year designing, fabricating, testing, and tuning this. This is a gigantic 4-foot wide FPV drone. This is part 2 in a build series where I designed nearly every part on this drone. Last video, I designed the motors and propellers, which if you haven't seen that yet, I highly recommend going to check that out. The link will be in the video description. In this video, we're gonna take those parts, design a frame, put it all together, and see if it gets off the ground. Thanks for joining me, stick around.
This project has been very challenging and often frustrating, but throughout the project I've been reminded that even though sometimes it may feel like quitting is easier, the big rewards come to those that never give up. So let's pick back up where I left off, where we need a sturdy and lightweight frame for this drone. After some research, I had a few ideas on how I could make this frame. This is my first design, and it was heavily inspired by this video, where this guy used polycarbonate plates, 3D printed TPU brackets, and aluminum arms. This design is 100% viable, and seemed to work well for the guy in that video, and polycarbonate would have been a very durable and affordable material choice, and actually, back when I was on a FIRST robotics team in high school, which I could make an entire video about, so I won't go into too much detail here, but we would use polycarbonate for all sorts of components, sometimes just panels to hold things in place, but we would also use it for parts that were going to be put in high impact situations, such as the ground intake that would often get rammed by other robots at high speed. The intake being made of polycarbonate allowed it to flex and then spring right back into shape. I decided not to go this route, mainly because I really liked the idea of almost every custom part being made on my 3D printer, and these plates would be perfectly suited for something like a CNC machine, but arguably, you could still make these parts with simple tools like a drill and a jigsaw. I also was pretty confident that I could design a lighter solution that could still get the job done. The next thing I considered was carbon fiber plates, like most X-Class frames, and most FPV frames in general. This, although, has the same issue of manufacturing capability as the polycarbonate, and paying someone to cut these parts for me seemed to be just a little bit more than I was willing to spend. With all of this information, what made the most sense in my mind is to just design a single 3D print that all the arms slot into. And to me, this seems like a cheap and easy solution that I can make right here at home. This design was my first physical prototype of the frame, and it didn't actually go so well. This day, my 3D printer was giving me so many issues. I was struggling with layer shifts, and the hot end temperature sensor was also having some issues. I think my printer is just wearing out. I've had it for a really long time, and it's printed a lot of parts. But nothing's gonna get in the way of progress, so I tried to push on with the build using the print anyway. Unfortunately, it immediately broke when I was just barely strength testing it. This is most likely because of that poor print quality, but it also showed me the weakness of this design. The square profile of the tubes makes corners in the print that create stress concentrations where the cracks can easily begin. We can avoid all the corners by pivoting the design to use round tube instead. And after I found out that round carbon fiber tubes are actually fairly affordable, I knew this is the route I wanted to go. This solves one issue, but presents another. With round tubes, the motor mounts are free to rotate around the tube, which could be catastrophic if this happens mid-flight. There are plenty of ways that this could be solved, but I went with the simplest solution I could think of, which is just to drill a hole through the tube and lock it in place with a screw. And for this design, my friend offered to print the center hub on his 3D printer, which came out absolutely perfect. Now, there is a lot of assembly to do, so let's roll a montage. As for the electronics for this drone, it's almost identical to any other FPV drone. It's just on a much larger scale, and consists of just a few basic components. Power starts here at the batteries, and in my case, I'm using two 6S batteries wired in series for a total of 12S, or about 50 volts. The S stands for how many cells are in series with each other, and these batteries have a clear outer case, so you can actually see the individual cells inside. The batteries are connected to the ESCs, or electronic speed controllers. These take steady DC voltage and turns it into 3-phase AC voltage. It can vary the current and frequency to precisely change the speed of the motors. The necessary motor speeds are calculated thousands of times a second by this. This is a flight controller. It's the brains of the whole operation. It uses a gyro and an accelerometer to determine what the 4 motor values should be to keep the drone in a specific orientation. The flight controller is sent radio stick commands from this receiver. The receiver also sends information back to the controller, like battery voltage, motor current, and signal strength. In my case, I'm also using a small BEC, which is just a step-down converter to power the flight controller, because the flight controller can't take 12S voltage, so I use the BEC to step that down to 12 volts. And as far as electronics, that's really all that we need to get the drone flying. So I then set up all the flight controller settings using a program called Betaflight, which is one of the most popular FPV drone setup tools. After some initial calibration, pairing the drone to the controller, making sure all the motors are spinning in the correct direction, and then doing a bit of wire management, I was ready to give it its first test flight. Okay guys, well, to say that I'm a little nervous would be a tremendous understatement. This is a lot of hard work that's gone into this, and it could all go catastrophically wrong if something was to go wrong. So we're gonna take it easy at first, and we're gonna cross our fingers that everything goes well. All right, I'm gonna mount up these props, and then we'll give it a test.
All right, let's test it out. So I'm gonna arm. I have a pre-arm, which means I have to push this button and then flick this switch to get it to arm. So if I just flick the switch, nothing happens. But hold the button, flick the switch.
I then did a basic pitch, roll, and yaw axis check, but I already started to sense something was a little off.
All right, here we go. I'm gonna raise the throttle very slightly. Okay. All right, the oscillations are really bad.
Yeah, the oscillations are pretty bad. And I tried again, but pretty much the same thing happened. So it didn't really fly. But why not? What went wrong? I mean, we made powerful enough motors, paired it with props that can make enough thrust, and made a lightweight and rigid frame. It doesn't make any sense. But actually, I have to be honest with you. You see, leading up to that first test, I was pretty confident that if by some miracle it was going to fly, it wasn't going to fly well. And that's because of something called PID control. I actually recorded myself talking about this topic multiple times throughout the build process. Now I will say, the PIDs are probably way off. I'm fairly confident that the PIDs are probably completely off. But I decided to cut all of that out because I thought a dedicated section of the video would make more sense. So I'm gonna do my best to give, you could call it a crash course on PID control. Boring! No, wait, don't listen to him. It won't be boring, just trust me, stick with me for a minute. PID is an acronym. It stands for proportional, integral, and derivative. And those words aren't really that important for you to know, but it's more important for you to understand what they do. The PID controller is a control algorithm that continuously compares the current position to the target position, and then calculates what needs to be done to be as close as possible to that target position. To achieve this, it's a bunch of math, but really what it's doing is it's taking an input, which comes from the joysticks on the controller, and feeds that into the PID control algorithm. The PID controller then calculates what the system needs to do. In our case, this is the motors on the drone. Then the system creates a physical output. This is read by the gyro sensor, and the output is fed right back into the PID controller. This happens over and over. You may have heard before the term PID loop, and this is why. Each letter in PID represents a value that we can change, that modifies the behavior of the drone. So what we need to do is change these values until the drone can stay in a perfect hover without going crazy. It sounds simple, but it's one of those things that's much easier said than done. You see, for most common-sized FPV drones, like ones with 3, 5, or 7-inch propellers, there's a whole slew of pre-made PID tunes that other people have made and tested. For most cases, you can just pick the one that best matches your drone build and you're off to the races. But my propellers are 18 inches in diameter and paired with custom homemade motors. I think it's pretty safe to say that there is no preset PID tune that's going to be right for this drone. So that leaves me with one option: tune it myself. And as someone that has never done this before, this sent me down a rabbit hole that was one of the most frustrating parts of this project. I spent days trying different values with no luck. I eventually realized that if I was going to hone in on the magic numbers that was going to make this drone work, I needed some data. Luckily, these FPV flight controllers come with a feature called black box logging, which can record all of the gyro data during a flight. On my flight controller, I need an SD card to write all the log files to, so I installed that and downloaded a couple programs that will allow me to view the black box logs. This, in theory, allows me to see if a change in the PID values makes a positive or a negative impact. But only a few flights in, I was looking over the log files and noticed something didn't look quite right. If you look at the diagram of the drone in the top left corner, you can see that over each propeller, there's a pie graph. This shows the motor throttle setting. Fully colored in means the flight controller is commanding that motor in ESC to 100%. If I scroll through the log file, you can see that there's one motor that is consistently hitting 100% while the other 3 are much lower. This is a huge problem and should not be happening. If one motor maxes out while the other 3 are not, this indicates something with that motor or ESC likely has an issue. At first, I immediately started thinking of all the things that could be the issue. I thought it could be an issue with my hand-wrapped coils, or maybe the motor has a bad batch of magnets, or maybe the ESC settings aren't right. The ESC settings would be the easiest thing to change, so that's where I went to first. I used an ESC configurator to change many different parameters and tested to see if this setting could at least minimize the issue. I found that the motor timing setting made by far the largest impact on performance. I plotted the results in Excel and found that 9 degrees of motor timing gave the best performance for my motors. It was actually crazy to see that only a few degrees added or subtracted would substantially affect the max power. After dialing in the ESC settings, the maxed out motor issue wasn't completely gone, but it was substantially better. Now I can continue PID tuning, knowing that all the motors still have some headroom in their throttle range. A defining feature of an FPV drone is the whole first-person view part. So far, I've just been operating the drone line of sight, but I thought it was time to kit it out with a real FPV system. This is just a simple analog camera and VTX module, and I have a love-hate relationship with analog video. If I had to describe analog video to you, it's like 1980s TV.
Where's the beef?
But the advantage is it's cheap, and I already have the analog goggles, so that's what I went with. Oh yeah, and I also mounted a camera on a long beam coming out the back of the drone, so you guys can have the best seat in the house. I think this view just gives an awesome perspective. At this point, I can tell the drone has enough power, but it is just so unstable and nearly impossible to keep in the air. Which makes sense because we never actually solved the PID tuning issue from earlier. So I got back to work testing different PID values, but no matter what I tried, I just couldn't seem to fix this. I've put in months of work into this project and still don't have a stable flying drone. You can imagine, at this point, I was feeling pretty defeated. Well, I'm out in the middle of the field running different PID values, trying to use PID Toolbox to fix this wobbling issue because it was really bad. It was really almost uncontrollable. But I mean, I was able to keep it in the air, but this is so frustrating. It's like you put in so much work into something and you get so close, but at the end, it's like I feel like I'm still so far away from the goal. I don't feel comfortable flying an FPV right now. I mean, I could barely even keep it in the air for like a few minutes. If I give it like a hard input to one side or the other, I mean, it goes absolutely nuts. I don't know what the problem is. I don't know if it's a PID value problem, but I've tried so many different PID values. That might be it for today, until I can go home and really figure out what the problem is.
Clearly, I was at a low, and a part of me just wanted to close the doors on this project and forget about it. But I was determined that the road to success of this project did not end here. So I took a step back and realized I may have approached PID tuning all wrong. Up to this point, I had been following along with most PID tuning guide videos, which say to adjust the PID sliders. This modifies the PID values in a relatively intuitive way. I had tried just about every combination of these sliders with no luck. But for one last attempt, out of complete desperation, I disabled these sliders and I manually set the P and D values way higher than the sliders allowed me to go. And to my absolute surprise, it actually started flying not too bad. Now look, I know it's not perfect. You can see some small jitters and wobbles, but it's flying, and it's actually very precise too. Every micro movement I make on the controller is correlating perfectly to the drone. I wanted to show some close friends and family members my newest creation, so we took it out to the park to really see what it can do. Well, there you go. Mission successful, right? Yeah, for a DJI drone. Come on, I can't put FPV drone in the video title from just that. FPV drones are capable of full acrobatics. Now, I don't want to put too high expectations for this drone. After all, it is nearly fully 3D printed and flying with homemade motors. But I had a thought from the start of this project that if the drone could do just one flip, one 360, catch itself, and land unscathed, I could call this project a success. So, with that possibly ambitious goal in mind, I decided to go for it.
Okay, we're gonna try a flip. We're gonna try a flip. I don't know what's gonna happen. Okay. Hopefully everything comes back in one piece.
Oh no, that's not good.
You broke a prop.
It's okay. Oh well, I'm sorry guys. I don't think it was in the right mode. I thought it was though. I really thought it was. I'm gonna pass it over. Yeah, it totally broke it off.
them.
Yeah, it ripped it off.
Dang.
It's all good. It's all good. I'm just gonna go cry now. You know, I think to an experienced person, it's easy to look at a project like this and see the faults, like how the drone shakes and wobbles a little bit when it flies, or how I wasn't able to achieve my goal of doing a 360 flip, or the fact that somehow I completely overlooked that the stator lamination plates in my motor from my last video need to be electrically isolated from one another, as many of you pointed out in the comment section. So thank you. But I look at this project and think about what once was an idea was brought to life into a beautifully detailed 3D model, and what once was a pile of raw materials, parts, and merely filament on my 3D printer was turned into a machine capable of flight. And how what once was a thought to make a YouTube video documenting the process of a project that I'm passionate about was made into a story capable of inspiring many people just like you. Hey guys, I just wanted to thank you so much for watching this video. I've poured my heart and soul into making this, and it means the world to me that you watched to the end. I know I left you on a bit of a cliffhanger there after the crash of the drone, so I thought I'd give a quick damage assessment to bring you up to speed. After the crash, the drone was in pretty bad shape. Every propeller had at least one blade that was broken, and one arm of the drone took kind of like the brunt of the impact, and that motor broke off its base, off its 3D printed base, and that carbon fiber tube had a small crack in it. The main section of the hub that all the arms slot into, that had multiple cracks throughout it. But since then, all the 3D prints have been reprinted and the drone is back up and it flies again. I haven't tried to do anything crazy yet, like do another flip, but it does hover. After reviewing the footage from the crash, I'm fairly confident that the main reason why it went crazy and started oscillating and fell out of the sky was because I did not have the controller in the correct mode. I know that's a silly mistake, but unfortunately that's what happened, I'm pretty sure. I was trying to put the controller in horizon mode, which allows you, like the center of the stick is basically acts like auto level mode, where if you let go of the stick, it automatically corrects and will stabilize. But if you were to put the joystick all the way to one side, it would do a full 360, and then once you let go, it would return. But I didn't realize it wasn't in the right mode because it kind of feels like angled mode when you're flying, small movements. And as soon as I threw the stick all the way to the side, it was in angled mode, so it went sideways, and then I let go and it just kind of went crazy and lost control. But is what it is.
It is what it is.
You also may be wondering, if you watched my previous video when it came out, why there's a 7-month upload gap. And you may be wondering, did it really take 7 months to make this video? And the truth is, no, but it also kind of did. The main reason for the delay is currently I am a full-time engineering student, which already takes an extraordinary amount of my time. So trying to work on YouTube and work on making sure I have good grades, it just seemed to be essentially impossible. I also didn't want to upload anything unfinished, so I just waited until I had enough free time in between school to work on this video. I do have some big plans and potentially wild ideas for future projects, so if you enjoyed this video and you'd like to see more like it, maybe consider subscribing. It's completely free. You can always change your mind later if you'd like, and it helps out the channel tremendously. And if you have any ideas for future projects, leave them down in the comments section. I read all the comments, so don't be shy.
One last thing I wanted to mention is that a lot of people have asked if the CAD files will be available for download for the motor and propeller from my last video, and I wasn't really sure what I was going to do at the time, but after thinking about it for a little bit, what I've done is I have exported all of the files, including the motor, the propeller, the frame, and even the master assembly, which includes all the electronics, and I've exported those in step file format and uploaded those to a Google Drive link. The link for that is down in the video description, so you can open that link and download all the step files. You can view them, or if you're brave enough, you can try making one of these motors and propellers, and maybe the whole drone. And if you do, please share it with me. I'd love to see it. I'd love to see other people's take on what I've done here. And I also feel like I have a duty to say that if you do decide to make one of these motors and props, please be careful. These motors are extremely powerful, and your printed props might not be exactly like mine, so your mileage may vary. So I think that's all for now. I just want to say thanks again for watching, and I'll see you next time.